Good morning, everyone. My name is Zahia Tigrine. I'm a researcher at Development Unit of Solar Equipment in Algeria. My presentation is about modeling and optimization of the performance of reverse osmosis desalination system powered by photovoltaic solar energy. First of all, I would like to thank all organizing members, especially Professor Hiba Abdullah and Professor Ayman Al-Jandi for invitation and for giving us this opportunity. And I express my honor and my pleasure to participate in your conference. This is my presentation outline. I will start with the introduction. After that, I will describe the materials and explain the method used in our study. I will then present the numerical results and reverse osmosis under construction and conclusion. Globally, 2 billion people now have access to safe drinking water, and 3.6 billion have no access to safely managed sanitation, according to the report published by UNESCO and on behalf of the UN Water. As this figure based on projection by the World Resource Institute shows 51 of the 164 countries analyzed are expected to suffer from high to extremely high water stress by 2050, which corresponds to 31% of population. Africa remains especially vulnerable to water-related tensions. 19 out of 20 states studied suffer from water scarcity, and 2/3 of the continent's freshwater resources are transboundary. By 2030, substantial increase water use efficiency across all sectors and ensure sustainable supply of fresh water to address water shortage. Desalination helps mitigate the impact of climate change, such as reduced rainfall and drought, which exacerbate water scarcity. It is a strategic and necessary response to the challenges posed by water scarcity in Algeria, and it allows the country to secure drinking water for its population and support the growth of its agricultural and industrial sectors. In Algeria, the projection of desalination plant amounts to 2.3 million cubic meter per day. Operating costs are mainly affected by the power or energy station, but the significant decreases in cost makes desalination increasingly competitive. The following figures show that desalination capacity demonstrated Algeria's commitment to using desalination technology to address its water scarcity challenges. The total capacity from both seawater and brackish water desalination plants help ensure a stable and reliable supply across the country. Among the different desalination technologies, there are 2 main processes processes based on evaporation, and other is based on membrane. Evaporation process can operate by heat supply, as in MSF multi-stage flash and multi-effect desalination, or through the supply of electric energy and by mechanical compression, vapor compression. Regarding membrane technologies like reverse osmosis, nanofiltration, or electrodialysis, they all operate by supplying electrical energy. Reverse osmosis involves forcing brackish water or seawater through a semi-permeable membrane that blocks salt and the other impurities while allowing fresh water to pass through. For operation, high pressure is applied to feed water, pushing it through this membrane, arrow membrane. The fresh water is collected on the other side, and the concentrated brine is discarded. For reverse osmosis, reverse osmosis system have lower energy consumption compared to the evaporation process, and can be scaled to various size, but membrane fouling and scaling require regular maintenance, and high quality membranes are very necessary. The main objective of our work are design, sizing, and optimization of ROPV desalination plant to meet the water needs for the Jama Al-Wad site, using EMS design software to determine the appropriate membrane and optimum configuration in compliance with the standards. And the optimization procedure is based on the selection of the minimum number of membranes and stage for a given feed rate. For working condition, we have production rate, flow rate is 1 cubic meter per hour, and quality of precipitation from Al-Wad region. And the plant operating modes is 4 hours per day, which with energy storage, operating temperature 25 degrees Celsius, and operating pressure varies between 5 and 14 bars. For modeling and sizing renewable electricity generator or solar PV, we have used the PVC software. Osmosis water treatment system consists in general of the pre-treatment, the membrane elements, and the post-treatment section. In the context of desalination, particularly reverse osmosis, pre-treatment is a crucial step to ensure the efficiency and the longevity of the air membrane. Proper pre-treatment helps to prevent fouling, scaling, or other issues that stop desalination processes, and can be divided into two main categories: water chemistry and physical pre-treatment technique. Post-treatment is used to achieve required product quality. Reverse osmosis system performance is typically characterized by two parameters: permeate flow or product, and permeate quality. These parameters should always be referenced to given feed water analysis, feed pressure, and recovery. We show here some configuration system that studied in our work. In our study, we have used the integrated membrane solution design software for designing and optimization aero membrane-based water treatment system. It allows us to simulate and predict the performance of different membrane configuration and operational condition. Salt water is considered the only natural water resources in this in the study area. Jama Al-Wad site situated in the south of Algeria, and the main objective of this project was to model and simulate water desalination by reverse osmosis in this region, where the physicochemical analysis of brackish water to be desalinated as shown are shown in this table, with the TDS equal to 4,445 milligram per liter, with electrical conductivity equal to 8,480 microsiemens per centimeters. In our work, different membrane type are tested and analyzed, namely ISPA2 LD4040, ISPA4, ISPA5, and LFC3 aero membrane. And various aero system configuration are tested as presented in the table. For example, scenario 2, we have two stage and one pressure vessel per stage and two membrane elements per stage. We have examined the effect of operating condition on membrane performance, recovery ratio, energy consumption, temperature, and TDS. The results of the modeling parameters measured in the region of wet soup are shown in following figures that illustrate the variation in TDS and energy consumption as a function of conversion rate for each membrane studied. This figure shows and summarizes the simulation results obtained. I mean, conversion rate, specific energy consumption, and total dissolved solids content for each membrane used independently. We note that specific energy consumption varies between 0.9 and 3.6 kilowatt per cubic meters for the four types of aero membrane, for conversion ratio between 20% and 60%. We also note that from a conversion ratio of 60%, energy consumption stabilizes and enable us to choose the right membrane based on this ratio. We note that or we found that the ISPA2 LD40 40 membrane has the lowest TDS value around 70 milligram per liters and an average energy consumption of 1.2 kilowatt per cubic meter compared to the other membranes. We therefore choose the ISPA2 membrane for aeronautics with its good water quality for the rest of our study. The results demonstrate, as shown, that the configuration 1, 2, and 3 using ISPA2 membrane consume the least energy. For technical reasons and the availability of materials, we have chosen configuration 3. The configuration used consisting of 4 stages with a pressure tube. Each stage comprises membrane elements connected in series. Results of chemical and after treatment with ISPA2 are presented in this figure. The comparison clearly demonstrates the effectiveness of previous osmosis filtration system in reducing the concentration of various undesirable chemical components in brackish water by achieving a reduction of over 95% for most parameters. The aero system ensures that the treated water meets high standard of purity and safety, making it suitable for drinking water, agriculture, or other applications. For example, we have hardness rejection and sodium and potassium rejection. In this slide, we show the numerical results obtained in configuration using configuration 3, representing the energy consumption and TDS for different feed water temperature values using ISPA2 membrane. The curve shows a progressive increase in TDS with increasing temperature. It can be seen that when temperature rises from 10 to 45 degrees, the TDS increases from 44 milligram per liter to 127 milligram. Analysis of the graph clearly shows that increasing the temperature leads to an exponential decrease in energy consumption in the reverse osmosis system. And temperature play a critical role in the performance and the maintenance of reverse osmosis system, while temperature can influence the solubility of salt and the permeability of membrane. High temperature can also have negative effects, and such as the formation of deposits or fouling and the promotion or development of biological growth. Here we present to you the reverse osmosis system that has been designed and is currently under construction. It will be coupled with to a photovoltaic solar generator with an energy storage system. Integrating a desalination plant with a solar energy system is a sustainable approach to that meets both water and energy needs.
Dr. Zahia, could you hear me?
The integration of energy.
Dr. Zahia, could you hear me?
I will. What? Yeah.
Could you hear me? Yes, we are now 15 minutes and we have very tight schedule. Could you please move to the conclusion?
Yes. Okay.
Thank you.
Just yes, we have make the medicine. We have just for the part of renewable energy, we must need 8 PV panels of 460 watt crate, one charge regulator, and of kilowatt. And given that the study has been aimed to evaluate an off-grid photovoltaic system to set up a solar reverse osmosis desalination system, the battery is essential to save energy and reduce the complexity of PV arrow system. As conclusion, integrating water desalination with renewable energies offer a promising solution for meeting drinking water needs in arid and remote regions. The study highlighted the importance of modeling and the optimization case system components such as the reverse osmosis plant and the PV system. And the use of specialized software for sizing and optimization has allowed us to obtain accurate results and design the optimum desalination system. And thank you.